Professor Indy, dealing with technology of dyeing one subject. Today, from the chapter 1, we are going to see the general theory of cellulosic and protein fiber structures. It is important to see the fiber quality, characteristics, and polymeric behavior related to dyeing. Many cotton species are grown commercially, but they may be conventionally divided into three types. Type 1 fibers have staple lengths varying from 25 to 60 mm, including high quality fine cottons such as the Egyptian, Sudanese and Sea Island varieties. Type 2 are coarser species with shorter staple lengths about 13 to 33 mm such as American upland cottons, and the type 3 species of still shorter staple lengths about 9 to 25 mm, commonly produced in various Asian countries. The mature cotton fiber forms a flat ribbon varying in width between 12 and 20 mm. It is highly convoluted, probably on account of the twisting that takes place when the tubular shape formed during growth collapses on the drying. The number of convolutions varying between 4 and 6 per millimeter, reversing in direction every millimeter or so along the fiber. Cross-sectional view of cotton fiber is kidney shaped, swelling almost round when moisture absorption takes place, as shown in figure A. This shape occurs from the inward collapse of the cotton fiber when it is dries out. The cross section tends to provide an indication of the relative dimensions of the lumen and fiber walls. Under the microscope, each cotton fiber is a single elongated cell that is flat twisted and ribbon-like with a wide inner hollow canals as lumen. These twists are also referred as convolutions as shown in figure B. Formation of convolutions occurs after the cotton ball bursts open. Then the limp simplified cotton seed hairs being to dry out and their cell walls collapse inward, which decreases the size of the lumen. Shrinkage, twisting of the cotton seeds hair results in the removal of the sap from the lumen and at least in the formation of convoluted fiber. Cotton fibers, as shown in cross section in figure C, their bean-shaped appearance is sometimes described as bilateral structures, which indicates that the density of packing of cellulose chains is not uniform across the fiber. Hence, the accessibility of the chain segments to various reagents varies across the fiber. Three main zones A, B, C, as it is shown in the figure, have been identified by means of enzymic degradation. The rate of the degradation increases from A to B and B to C, which is the order of decreasing the density of packing. Between zones A and C, there appear to be limited areas as denoted by N, even more accessible than zone C. The convolutions and kidney-shaped cross-section of the cotton fiber enable it to make only random contact with the skin, which is more comfortable and compatible to human skin. Moisture absorption of cotton fiber is due to the countless minute air spaces which exist because of the convolutions and kidney-shaped cross-section of cotton fiber, thus making them more comfortable to wear. Circular cross-sectional shape imparts stronger luster to the fiber or filament because of the incident light is reflected so evenly. This tends to result in a rather harsh, strong luster. Harsh luster is because when the fiber or filament may be twisted in the yarn or fabric, its circular shape allows reflecting the same amount of incident light despite the unevenness of its reflection. The irregular shape results uneven reflection of light, so the luster of the fiber will be very poor. Therefore, in pre-treatment of the fiber, the cross-section is made circular. Convolutions are also removed so that more even surface may be given more lusters. Microstructure of the cotton fiber. The cotton fiber is single plant cell. It has the distinct cuticle, well-developed primary and secondary walls and the lumen. The cuticle is the outer waxy layer, exists very outside of the cotton fiber. Cuticle consists of pectins and proteinous materials. It serves as a smooth, water-resistant coating which protects the fiber from chemical and other degrading agents. The waxy nature of the cuticle enables it to adhere tenaciously to the primary wall of the fiber. This layer is removed from the fiber by scouring process. The primary wall is the original thin cell wall which is immediately present underneath the cuticle. It is 200 micron thickness. It mainly consists of cellulose or network of small strands of cellulose called fibrils. The fibrils spiral at about 70 degree to the fiber axis. This spiraling imparts strength to the primary cell and hence to the fiber. This makes for a well-organized system of continuous, very fine capillaries. The fine surface capillaries of each cotton fiber contribute greatly to cotton's wipe-dry performance. The secondary wall layers of cellulose consist of concentric layers present beneath the primary cell wall, which constitutes the main portion of the cotton fiber. After the fiber has attained its maximum diameter, new layers of cellulose fibrils are added to form the secondary wall. Its fibrils are about 10 micron thickness, but of undefined length. Near the primary cell wall, the fibrils of the secondary wall spirals at about 20 to 30 degree to the fiber axis. The fibrils are packed close together, again forming small capillaries. As the fibrils changes the direction of their spirals, a weak area exists in the secondary wall structure, which results in weak areas are responsible for alteration of the direction of the twist of the convolutions. The lumen is the hollow canal that runs the length of the fiber. It is filled with a cell during the growth period. The lumen was once the central vacuole of the growing cotton fiber. After the fiber matures and the ball opens, the protoplast dries up and the lumen naturally collapses, leaving a central void in each fiber. When the sap evaporates, its constituents remain behind to contribute to the color of the cotton fiber. As the sap evaporates, the pressure inside the fiber becomes less than the atmospheric pressure on the outside. This caused the fiber to collapse inward, resulting in the bean or kidney-shaped cross-section of the cotton fiber. Cotton fibers have a fibrillar structure. Their morphology illustrated schematically in the figure. Three main features, that is primary wall, secondary wall and lumen. The primary wall consists of a network of cellulose fibrils covered with an outer layer or cuticle of pectin, protein, mineral matters and wax. The wax renders the fiber impermeable to water and aqueous solutions unless a wetting agent is present. The secondary wall constitutes the bulk of the mature fiber and consists almost entirely of the fibrils of cellulose arranged spirally around the fiber axis. The direction of the spiral reversing, changing between S and Z twist many times along a single fibril. Reversal points frequently correspond with a reversal of the exterior convolutions. The secondary wall consists of several layers and the spiral angle of the fibrils varies from one layer to the next from about 20 to 35 degrees. Although fibrils may be seen under a high power microscope, there is considerable uncertainty about their dimensions. The resolution limit of the optical microscope is around 0.2 millimeter, but the fibrils seem to be bundles of smaller microfibrils which appear in the electron microscope to be 0.02 to 0.03 millimeter thick and at least 10 millimeter long. The microfibrils are themselves believed to consist of still smaller elementary fibrils that are approximately 0.004 to 0.006 millimeter in cross section. Cotton is linear cellulose polymer. The repeating unit in the cotton has two glucose units called cellubiose. Cotton consists of about 5,000 cellubiose units. Its degree of polymerization is thus 5,000. Its degree of polymerization is 5,000 means 5,000 repeating units. Hence, it is a very long linear polymer about 5,000 nanometer in length and about 0.8 nanometer in the thickness. The most important chemical group on the cotton polymer are the hydroxyl groups, that is OH, which are also present as methylol groups, that is CH2OH. Due to the presence of hydroxyl groups, polar nature of the polymer gives rise to hydrogen bonds between the hydroxyl groups of Adjacent cotton polymers. Polymer system of cotton is crystalline in nature. It consists of about 65 to 70% crystalline and about 35 to 30% of amorphous regions. Polymer system of cotton shows well-ordered and oriented crystalline regions. The maximum distance across which hydrogen bonds can form between polymers in 0.5 nanometer in crystalline regions. Hydrogen bonds are the dominant forces of attraction present in the polymer system of cotton. Van der Waals forces, which are also present, have little relevance. The polymer system of cotton can be imagined as a roll of wire netting. The crystalline regions are therefore the well-ordered lines and rows of hexagonal holes of the wire netting. The amorphous regions are the disarrangements of these orderly lines. Thus, the cotton fiber consists of an assembly of fibrils in which the cellulose is accessible to most reagents only at fibrillar surfaces by way of a system of voids and channels. The crystalline fibril concept of the fine structure of cotton has been further refined by Rowland and Roberts. Some surfaces which are shown in the form of A of the elementary fibrils are so close to one another that they are inaccessible to all chemical reagents unless swelling has been induced. Others, B, are relatively disordered and are more accessible. In addition, there are readily accessible surfaces C in the tilt twist regions of that connect the more ordered regions. It is instructive to compare the composition of the primary wall with that of the cotton fiber as a whole, since it is the primary wall that becomes disintegrated when preparing cotton for dyeing and printing. Although the primary wall accounts for only 5% by weight of the fiber, it contains most of the non-cellulosic constituents. As it is shown in the table, it gives the comparative data for a typical cotton fiber. The other substances are mostly water-soluble organic acids and sugars. This table also illustrates the very high cellulose content of cotton, which surpasses all other natural sources in this respect. Now, after cotton, we will see about wool fiber. Wool is the natural protein fiber from the fleece of domesticated sheep. The main wool classifications are full fleece, that is year's growth, second shear, and early shorn, that is part year's growth, and crutchings. The macro structure of wool. The wool fiber is a crimped, fine to thick, regular fiber. Fine wools have as many as 10 crimps per centimeter. while coarse wool has less than 4 crimps per 10 centimeters. As the diameter of wool fiber increases, the number of crimps per unit length decreases. The number of crimps per unit of length may be taken as an indication of wool fiber diameter or wool fiber fineness. As the diameter of the wool fiber increases, the crimp per unit length decreases. The crimp configuration prevents wool fibers from aligning themselves too closely when being spun into yarn. As a result, it is possible to have wool textile materials with air spaces occupying about two-thirds of the volume. The warmth of wool fabrics is due more to the air spaces in material than to the fibers. Length of the fiber ranges from 5 cm for finest to 35 cm for the coarsest wool. Diameter for the finer 14 micron and for coarsest 45 micron. Length width ratio ranges from 2500 as to 1 for the fine and shorter and 7500 as to 1 for coarser and longer. Colors vary from off-white to light cream. Color of wool varies due to the disulfide bonds which acts as chromophores. As a result, the incident light may be modified to cause the reflected light to have a tinge of yellow, giving the wool fibers their off-white appearance. When the fiber is cream to dark, it cream in color. This is due to more polymer degradation on the surface of the fiber, as wool polymer is very sensitive to atmospheric oxygen and air pollutants. This is microscopic appearance of wool. Longitudinal microscopic appearance of wool is the overlapping surface of cell structure. These surface cells, known as epithelial cells and commonly known as scales, which point towards the tip of the fiber. The cross section of wool fiber is usually oval in shape. The felting of wool is the irreversible shrinkage of the length, breadth, and thickness of the material. Wool felts because of the serrated surface of its fiber, which is formed by the overlapping epithelial cells or scales. Because of these serrated structures, less friction will result in the fiber moves in rootwards direction than if it moves in tipward direction. This difference in surface friction between the two directions is known as the directional frictional effect. Felting of fiber is enhanced by heat, acid, or alkali. The microstructure of wool fiber consists of three main components of the cuticle cortex and medulla. The cuticle is the layer of overlapping epithelial cells surrounding the wool fiber, and there are three cuticles. The three cut- the cuticle is the layer of overlapping epithelial cells surrounding the wool fiber. There are three cuticle, one epicuticle. The epicuticle is the outermost layer covers of the wool fiber. Exocuticle, the overlapping epithelial cells forms the exocuticle, and endocuticle, it is intermediate connecting layer bonding the epithelial cells of the cortex of the wool fiber. The cortex of the wool fiber is the core of the fiber, forms about 90% of the fiber volume. It con countless long spindle-shaped cells or cortical cells. It is composed of two regions known as ortho and paracortex. The orthocortex absorbing more dye than paracortex. The orthocortex and paracortex spiral around one another. Fine wool fibers have about 20 such cells, whereas coarser wool fibers have about 50 cortical cells across the diameter of their cross section. Then medulla. Coarser fibers have hollow space running lengthwise through the center. This is medulla. The wool polymer is a linear alpha keratin polymer which has a helical configuration. Steps in the formation of wool polymer are not known. So, the repeating unit of wool polymer is amino acid, which is linked to each other by the peptide bonds CONH groups. As a result, it is not possible to determine the extent or degree of polymerization for wool. It consists of a long polypeptide chain constructed from 18 amino acids. The wool polymer is about 140 nanometer and about 1 nanometer thick. It is normal relaxed state. The wool polymer has alpha keratin structure. Stretching of the wool fiber tends to straighten with unfolded configuration called beta keratin. A beta keratin wool polymer always tends to return to its relaxed alpha keratin structure. The amorphous region of wool polymer system is extremely amorphous in nature, as it is about 25 to 30% crystalline. The spiraling of the protofibrils, microfibrils and macrofibrils does not imply a well-aligned polymer system. The complexity of the wool polymer is due to important chemical groupings it contains and the interpolymer forces of attraction. There are many bonding between the polymer, in which the first, the polar peptide groups, the oxygen of carbonyl group is slightly negatively charged, as a result will form hydrogen bonds with the slightly positively charged hydrogen of the amino groups, that is NH, of another peptide group. The second is salt linkages or ionic bonds. Carboxyl radicals COOH and NH2 groups of amino acids, which are basically the acidic and basic groups. Salt linkages or ionic bonds are to be formed. The third, covalent bonds. The cysteine, the sulfur containing amino acids which is present in the wool, makes the wool polymer system the only one with cysteine linkages, also known as disulfide bonds. Cysteine bonds are covalent bonds. They occur within and between wool polymers. And also the van der Waals forces are acting a role in the wool polymer. Wool is composed principally of proteins which are polycondensation products in which the different amino acids are linked together to form a polypeptide chain. They possess a large number of highly polar peptide linkages which can give rise to inter and intramolecular hydrogen bonding. While these bonds contribute much toward increasing the strength of the fiber, such close spacing of these groups along the molecular chain would be detrimental to other desirable fiber properties. They contain relatively large side chains groups in the scheme of the polypeptide chain, which prevents close packing of the protein molecules and thus decrease the extent to which hydrogen bonding can occur. The low tensile strength of wool is due to the relatively few hydrogen bonds that are formed. Now, the silk fiber. Silk polymer is a linear fibroin polymer. It is composed of 16 different amino acids. The silk polymer is not composed of any amino acids containing sulfur. So it does not contain any disulfide bonds. Silk polymer occurs only in the beta configuration. Length of the silk polymer is about 140 nanometer, which is slightly longer than wool polymer, and about 0.9 nanometer thick. The important chemical groupings of the silk polymer are the peptide groups, which gives rise to hydrogen bonds, and the carboxyl and amine groups, which give rise to salt linkages. Polymer system of silk is composed of layers of folded linear polymers. This results in 65 to 70% crystalline polymer system. The major forces of the attraction between silk polymers are hydrogen bonds, which are effective across the distance of less than 0.5 nanometer. This ensures that fibrine polymers must be closer than this given distance. The cross section of raw silk is roughly elliptical. As it is shown in figure, the triangular twin fibrine filaments covered by sericin face each other. The beauty, softness and luster of silk are due to triangular cross section of the silk filament. After degumming process, twin fibrine filaments separates into individual filaments, giving finer and more lustrous fiber. It lacks longitudinal features along the longitudinal section. The appearance of silk filament when we discuss, so silk filaments are 600 to 1700 meter long and diameter ranges from 12 to 30 nanometer depending upon the health, diet and the state under which the silk larva extrudes the silk filaments. So fiber length to breadth ratio is 2000 to 1. It is off-white to yellow in color. Hygroscopic nature of the fiber. The moisture region of silk is about 11% compared to cotton, which has 10.5%. This is due to the very crystalline polymer system. The amount of moisture absorbed by the silk depends on whether it is raw, degummed silk or on the species of silk and in the humidity. The mechanical properties of silk is a stronger fiber. A filament of silk is stronger than equal diameter of the steel filament. This strength is due to the linear beta configuration polymers and very crystalline polymer system. These factors lead to formation of many hydrogen bonds in a much more regular manner. When fabric is ready in the weaving department and then it is taken for the pre-treatment, before coloration, some characteristics or some parameters has to be satisfied from the fabric. Then only such a fabric is suitable for the chemical processing. First, the length of the fabric is important to make the batch sizes. Then width of the fabric. So all even width fabrics are stitched together and making a very long batch. Then thickness of the fabric. Then all calculations of chemicals are done on the weight of the fabric. That's why weight per unit area of the fabric is more important. Then on that basis the weight per unit length of the fabric is also important. Then fabric strength and extensibility, so tensile strength, because in pre-treatment many of the time some strength losses are taken place. So desired strength at the end use of the fabric, how much is required. By considering the strength losses during the pre-treatment, it has to be considered that the initial strength of the fabric should be slightly higher than the desired strength of the end use. Then tearing strength, in that also the tearing strength, how much is required after the processing. So before that the tearing strength should be somewhat more in form of a gray fabric. Then ends per inch, then peaks per inch. For certain quality of the fabric, always the complete batch it should be the same. Then warp count and weft count, these are also important because variation in these counts also varies the quality of the fabric. When gray fabric taken for coloration, such fabric requires some quality which are shown here. The crimp, the warp crimp and weft crimp of the fabric, then handle, stiffness of the fabric, drape of the fabric, then crease resistance and crease recovery properties, then air permeability, abrasion resistance, water resistance, shrinkages, then different fastness properties, fastness to light, fastness to wash, fastness to perspiration and fastness to rubbing. All these characteristics are depends for which the fabric is taken for which end use purpose. As a own fabric, some qualities were required, so it is also required in case of knitted fabrics. In case of knitted fabric, strength and extensibility, then coarse density, Wells density, then loop length, then elasticity of the fabric, then deformation tendency of the knitted fabric, then grams per square meter GSM, and yarn count, and design, actually which type of loop arrangement is taken. So all these characteristics should be even through the complete length of that fabric, and such similar fabrics are stitched together to make a one batch. Have a nice day. See you in the next lecture.